such disturbances are bound to occur because I cannot say that the seminar hall 1 will be used exclusively by the mechanical department on every Tuesdays and Thursdays. We have to accommodate other. There is a visiting professor from Japan who is delivering a lecture there, so we may have to accommodate. So such disturbances are likely to be there whenever there is someone standing outside directing you to hall number 2, because again there is another program on March. So you may have to adjust. Coming to today's program, today we are going to discuss your assignments. For aeronautical I have corrected few, but I thought I would correct in your presence, and then I have stopped correcting. Okay, because I see many just downloaded materials, which I am going to award only 0. So if just downloaded material doesn't deserve any marks, and we are going to be merciless in evaluating. So I thought I will correct in your presence. So probably tomorrow afternoon you can come, I will correct it and then finish it. But since this assignment is going to be part of your first assessment, questions might be asked from these assignments also. So I thought I should discuss before we conclude the portion for the first assessment. The portion for the first assessment is up to the voice of the customer. Whatever we have discussed, up to the voice of the customer, plus assignments is the portion for the first assessment. And on coming Tuesday, we will have a guest lecture from an industry. There is a company called Design Desk India Private Limited. Their core competence is in reverse engineering. So the Chief Executive Officer of BDA will be coming and delivering a lecture on 3rd. And it will be for 2 hours, and the lecture will be on reverse engineering. So whatever is discussed in the class plus guest lecture, everything will they will form part of your first test push. Now coming to the analysis of failures. First of all, why should we analyze these failures? That question needs to be understood thoroughly. Why should we analyze these failures? These are all some of the major engineering failures, no doubt about it. But the basic question is, why should we analyze it in detail? What is the basic approach? Why should I bother about these failures? This has happened long back. Because, in my perception, these failures ought to be analyzed because these are failures of engineering design essentially. See, one of the big expectations of a design engineer is he is supposed to foresee everything. Okay, he is not a fortune teller. A design engineer is not a fortune teller, but he is supposed to foresee every conceivable mode of failure and then fortify his product against such failures. That is the real challenge before the design engineer. It is always easier to pinpoint some mistake in retrospect. After something has happened, hey, you should not have done this, you should not have done this. It is easy to say. But the real challenge before the design engineer is he should foresee that in advance and then fortify his product against such shortcomings. After something has happened, it is always very easy to pinpoint a mistake, to attribute these failures to this person or that person or this incident or that incident. But the real challenge before us is how to foresee these failures, okay, and then safeguard our product against these failures. And as a result of these studies, all these studies, we are going to learn three important concepts. Two I have given to you already. One is the idea of redundancy. The other is the idea of factor of safety. The third concept I will explain at the end of my lecture. It is on safe fail and fail safe. The idea of safe fail and fail safe. So these three ideas we will discuss in detail. So as a summary of all these discussions, we are going to learn three important design ideas. One is the factor of safety, the other is the redundancy, the idea of factor of safety, the idea of redundancy, and fail-safe and safe-fail designs. So, what I thought was, I thought I will discuss all the failures in detail, but that will be beyond the scope, because doing justice to each of the failure will take at least 1 hour. So what I thought was, I will take one case and then discuss in detail. Okay, doing full justice to it, so that you can look into your own problems and then reanalyze your own assignment. Is it okay? So because this has happened very recently, I have chosen the Deepwater Horizon oil spill, which is a British petroleum disaster. Okay, next slide please. Now this is the topic I am going to discuss in detail. What exactly happened in Deepwater Horizon oil spill? And this is the oil rig that failed completely. I have included this image to help you people to understand the size of an oil rig. Okay, please see the size of the oil rig. You can see the boats around, small ships around. Okay, it is a mammoth structure. It is a floating structure. Okay, and it is supposed to exert a lot of force, and then it is supposed to drill the oil wells. Next slide please. Sir, can you remove that slide show? Yes. Yes. Now what happened was, on April 2010, methane gas from the exploder, as you all might know, any oil well, the oil well naturally contains the oil, and it is volatile. So the low boiling point constituent of any oil will evaporate and fill the cavity. Typically, I don't have a blackboard today. Typically, an oil well will be roughly a space in the earth's crust. Okay, it is a sort of void inside the earth's crust. In fact, it is very interesting to look at how that void itself would have formed. This is one of the topics of research for geologists. How can you get a huge void inside the earth's crust? Now it is actually, as you might know, these are all biological species that got decayed into oil and gas. So as this biological species, they decay, they shrunk, leaving some gap. Okay, and subsequently they got covered by the layers of sand and layers of earth, and subsequently even water. Okay. Now, any oil well, it will be almost half filled with oil, and the remaining space will be filled with gas. Typically, it is natural gas. The main constituent of the natural gas is methane. Generally, whenever you drill oil oil, you have to let out this methane gas outside. You let out this natural gas outside because people at some point of time thought that natural gas is not economical to tap and use. So what they will do is they will erect huge chimneys, the natural gas will come out of it and it will naturally burn. Because as it enters into the atmosphere, it gets into contact with oxygen and it will burn. Recently, in many countries, people have said natural gas should not be let out like this because methane is worse. Methane is not poisonous, not hazardous. You are letting out in very high atmospheric level. It is a ozone depleter. Methane is a very strong ozone depleter. So as methane escapes out, okay, it is going to drill holes on the ozone layer. Okay, so it will cause a lot of other undesirable effects, and that is why people said you should not let out methane. You should use the natural gas. Okay, Delhi, the High Court, it ordered that all the transport buses must run with natural gas only. All that is happening all over the world, not only in India. Here, what happened was, when the drilling was carrying on, can you go to the next slide, please? That will give you some idea. Yes. So this is the sort of schematic view of the drilling that we saw. You can see that it has helipad, all that. You have lifeboats here, which were used subsequently for the people to escape. You have a helipad. Now from here, they are drilling the ocean floor. Can I have the next slide, please? No, next. Leave it, go back. Sorry, I didn't have that image, go back. Okay. So from the ocean, from the sea level, the ocean floor at this particular place is roughly 1,500 meters down. The ocean floor is, because all these numbers, they have an important bearing on what we are going to do subsequently. From the water level, the ocean floor is 1,500 meters down, and from the ocean floor, the oil deposit is around again another 2,500 meters down. Okay, so as they at the ocean floor level, one of the important component of offshore drilling structure is a huge device called a blowout preventer. Okay. Now the failure at this particular plant, at this particular rig, is exactly at the blowout preventer. Blowout preventer is a huge structure. How can I say? I can say it will be something like a three-story building, a three-story house. Okay, a blowout preventer. It is about 15 meters high, and then it will be a huge structure. So the purpose of a blowout preventer is to precisely prevent the oil and gas escaping out of. It is a sort of, basically it is a valve. When I say it is a valve, it is a 15 meters high valve. Okay, we should get used to this size because these are all engineering designs. It is a 15 meter high valve. Essentially, it is supposed to prevent any blow, any uncontrolled emission of gas or oil. It should not happen. And this blowout preventer is located at the floor level. Do you understand what I mean by floor level? At the ocean floor level, that is 1,500 meters below the sea level. Is it okay? Can you go back to the previous slide? So on April 2010, methane gas from the well exploded into the drilling riser. It should not have happened. And then, as methane came into contact oxygen in an uncontrolled fashion. The methane was under heavy pressure, so it immediately exploded. All the operators of the drill jig, but for 10, escaped through the lifeboats. Till date, we don't know what happened to those 10 people. Neither their body, nothing could be traced till date. Okay. But for those, the others escaped using the lifeboats because the whole drill jig is under fire. Now the drill jig it was in flames and it sank after 36 hours of burning. I put it 36 hours because nothing could be done, could not be extinguished. It completely burned and then subsequently it got sunk. It is in sea, there is no depth of water. It can be accessed by helicopters. Many ways. They tried everything. Why it cannot be extinguished? Because there is continuous. The whole idea is this fire, it could not be extinguished because there is a continuous supply of fuel, not oil. At that point of time, not oil, much more dangerous, gas, and it is gushing out at a very fast rate. Oil comes much later. Now the oil started coming out of the drilling riser. It happens much later. Next slide. So this is the sketch of the whole arrangement. Next slide. Now this is the oil that is coming to the shores, and this is a beautiful picture of a seabird whose feathers are soaked in oil. It cannot fly, it cannot do anything. It has to find its death in a very painful way. Okay, because the whole it is a very cruel way for a seabird to die because its feathers are coated with oil. So if the feathers they have wax coating so that it never gets wet. But this wax coating is ineffective against oil. So it is coated with oil, the wings become heavy, it cannot fly. So this is a single picture, they are quite popular. Many of you might have seen it already, which depicted the cruelty of what has happened to the environment. The bird has to die. It's not a one bird dying, it is thousands. And what is the volume of oil that is gushing out? It is 10,000 cubic meters of oil per day. You know what the volume? 10,000 cubic meters, roughly you can say 1 cubic meter is 1,000 liters. Approximately. You want to take 10%. Okay, 1 cubic meter is 1,000 liters. 10 million liters every day of oil gushing out, and that is a huge amount. The whole seashore became spoiled, and as the churning of the sea takes place, this oil, all the low boiling point constituents will get evaporated, and the tar balls they get deposited on the shores. On the shores mostly we get tar balls because all the lower melting point constituents they will get evaporated. The blackish tar balls will be thrown onto the shore. Seeing a tar ball is an indicator of oil spill. It has happened in Mumbai, it has happened in all seashores. Please remember, this is not the first oil spill accident. There is a huge list we have. Next slide. What is the technical challenge? So what? Something wrong has happened. But what is the engineering challenge in this? What is the basic engineering difficulty? The blowout preventer has failed. Fine. The blowout preventer has failed, yes. Now, the basic problem is, it is just a plumbing problem. What do I mean by a plumbing problem? In your house, have you ever seen a pipeline getting burst? Yesterday Mr. Mani will work for it. Yesterday in the Singh laboratory, the compressor pipe got burst. there was a huge sound. I don't know, some of you might be working in the neighboring labs would have heard it. There was a huge sound because the pipe which is coming out of the compressor, it got burst. Right? So what we did was, we closed the compressor valve, the sound immediately stopped. Mani rushed to the spot and he and Tamil children, they closed the compressor valve. The airflow had stopped. They took out the tube. They removed some about a feet length of the tube. They connected it back. Everything is back into operation. The compressor was switched on immediately. Yes?
Yes, sir.
Compressor was switched on immediately. The whole problem was solved within 5-10 minutes. The problem is very similar. It is a plumbing problem. Basically, there is some damage, not in the pipeline, but in the valve. It's like some piping line getting burst in your house. What will you do? You will go further. You will trace back, find a valve, close it, so that there is no more loss of water. Cut the required portion. Cut the portion which got damaged. Replace it. So what is the big issue? The big issue is the whole thing is happening at 1,500 meters below the sea level. Otherwise, it is not an issue at all. See, an engineer has to pinpoint where the real difficulty lies. If the whole thing is happening somewhere else, it is not an issue at all. A regular plumber would have solved the problem. But here the pipelines are huge. That's all. But what is the difficulty? The whole thing is happening at 1,500 meters below the sea level. So what? So what? If it is 1,500 meters below the sea level, what is the difficulty? The difficulty is the water pressure itself is 150 bar. What do you mean by 150 bar? For a comparison, the tire pressure in your vehicle is about 1.8 bar. It is almost 100 times the tire pressure that you have. Okay, imagine the force with which the air is injected into the tire. It is almost 100 times more pressure. Now, the size of the oil escape preventer is under pressurized oil gushing out, because see, it is like the reservoir is now like a balloon. The whole water pressure it again pushes this reservoir, and then the oil is gushing out at huge pressure, and these are the other issues. So you appreciate what is the technical challenge that you have. The only challenge is, or I would say the single most important technical challenge after this has happened is the huge pressure at which any operation is to be carried. As you will see, in all the subsequent measures, they tried many ways of putting some seal to this leakage. In all these measures, you will identify these technical challenges posing big problems. Next slide, please. Now, what they tried to do was, the first attempt was the top kill. Now suppose oil is gushing out of some well. Okay. Now I should find some local material with which this whole process is to be stopped. Now what I do is, the first attempt was to seal the whole flow, through the blow preventer. Now what they did was, using huge compressors, if they could generate enough pressure, to carry debris and then dump it into the oil well. So that you cover the entire oil well with something which is solid. You choke. You choke it so that the oil will not come out easily. Okay. They tried with whatever is available around. Okay. What is readily available in an offshore drilling rig is the drilling mud. Okay. They try to choke it and it will merge well with the atmosphere. So they can use it to just choke the well. It couldn't work because you have to generate enough pressure, and that pressure has to overcome the oil pressure. It didn't happen at all. They couldn't succeed. Next slide, please. Then they tried with what is known as a containment dome. So this is the area of problem. This is where the leakage is occurring. What you do is they took a bell-shaped dome. So they first contain it to the bell-shaped dome, so that oil won't go spontaneously. Okay. In fact, what happened was, see, the oil pipe was a freestanding structure. I cannot have a support. You have the ocean floor, this is the water level. I am drilling a jig. As you keep on drilling, like your boat drilling, they will be putting a pipe. This pipe is a freestanding structure from the ocean floor to the water level. Now this freestanding structure, after the rig has gone, it collapsed. Okay, this way, because there is nothing to support. It is a tube standing for 1.5 kilometers high. So it cannot stand on its own. It got sagged and then it broke in 4-5 places. So it is lying as a debris. Now what they did was they wanted to have a containment zone. They first tried to choke the pipe itself. They couldn't succeed. So they tried to have a containment zone within which the whole damage could be controlled, and subsequently you can either pump out oil from this or do whatever you want. But this also didn't work. This could not also succeed. This is the C4 level, and this is the area through which the water and the oil will be collected here, and from this you can put some piping, extract it, do whatever. This again couldn't work because of the high pressure involved. Materials to withstand 150 bar. See, this physical 150 bar pressure, I don't know, you might have seen your LPG gas cylinder. Okay, the cylinder is made up of very thick material, believe me. The pressure there, it will be around 12 bar. I don't remember the exact value, but it will be around 12 bar, 12.5 bar. Okay, that is the pressure there. So to have a 12.5 mm bar pressure, you have to put about 12 mm thick of steel. So to take up such a huge pressure, to develop a material itself is a big challenge. They did it, but this didn't succeed. The next attempt, of course, this led to some solution. Next slide, please. What they did was, they started constructing the relief wells at two neighboring places. This is the entire timeline. So that is where the oil leak is taking place. So what they did was, so you have a leak taking place at a particular place, go down, tap all the oil and take out through some other route. Okay. So after that, after you have provided some relief of the internal oil pressure, I can do anything I want. If the oil is not gushing out at huge pressure, probably I can retry top fill, I can retry a containment dome, and this what had finally worked. You have to put a relief path. And please remember, where does it meet? It meets about that is 5,000 feet, 5,000 meters from the sea level. It has to go 5,000 meters from the sea level. This is 1.5 bar. This is 1,500 meters, and this is again another 3,500 meters. Okay, this is where it has to meet, and the reservoir is still down. I cannot go to the reservoir because if I go to the reservoir straight, then oil will start coming out through this. So they have to intercept it just above the reservoir so that you just take it out. Subsequently, the pressure here will get eased and I can do whatever containment I want at this particular point. So that's how. See, you understand what is the one? The whole pressure, the water pressure itself. It is the first biggest challenge. You cannot just like that send a plumber with a dive suit and then he will go there. No, nothing will work. By the sheer water pressure, any amount of protection you take, and there are very few submarines that can reach. Special submarines are required to withstand such. Normal submarines cannot go this deep. Special submarines are required to go to these particular depths. Okay. So the sheer pressure of the sheer pressure of the water and the oil pressure which is gushing out, these are the twin issues that pose a huge challenge, so that the relief could not take place easily. Next slide please. Now, before I go back sir, we'll come back to this slightly later. Please go back. Now, before I go into other details, probably I'll spend 5 minutes on two more cases. First, we will talk about Fukushima accidents. In fact, these accidents, they shook the entire world. All engineers, all engineering students must know that Japanese are the people who are very conscious about quality. So in all their work, over the past 50 years, they have been very conscious about quality. And they were supposed to follow the rules very strictly. People used to say all these stories. Okay, even if there is no traffic, they will wait for the green light to cross the road. Even if absolutely no traffic on either side, the Japanese will wait. Even I mean, that is the culture of the Japanese people. Even at extreme situations, they will panic. They will go to supermarket and queues, and then even when there was food shortage, all that is true. But when such accidents took place in the nuclear power plant of Fukushima, it raised many eyebrows. Now what happened was that the problem is, I'm not going into the details, all of you might know it, you might have heard about it. To put the details in short, earthquake and tsunami happened simultaneously. Earthquake and tsunami happened simultaneously. Now there is no power. Okay, the tsunami ensured that because of earthquake there is no power, and the tsunami ensured that the generators also will not work. So the problem was pretty simple. The nuclear reaction is taking place inside the dome, and it generates enormous amount of heat. This heat this energy is to be taken away by some means. The energy generated by the nuclear fission is to be taken away. Otherwise what happens? If you don't take away the energy, the heat inside will increase. The heat generated inside the reactor zone will increase and it will melt the uranium rods. Molten uranium is highly reactive. Okay, it will penetrate any metal, it is very reactive, and it will induce an uncontrolled chain reaction. So molten uranium is highly reactive, so it cannot be contained. The first problem. Number two, because see, any material, they become more reactive at elevated temperature. I think we saw it in the previous class also. Any material will become more reactive at any chemical reaction will become more vigorous at elevated temperatures. Uranium will become very extremely reactive at molten state, and it cannot be contained by any material. Okay, and it will lead to uncontrolled chain reaction. So what is the technical issue now? Now there are two issues that are to be analyzed in such situations. What would have prevented the accident? What would have prevented accident? I will come to that a bit later. In a generic sense, not on a specific case basis. But after the accident has occurred, what is the technical challenge? What is the engineering challenge before us? After the accident has occurred, the specific engineering challenge is you have so many heat generated, so much of heat generated, how to dispose it off, how to take it away. So one is using some closed loop water circuit. That is what they were trying. In fact, they tried too hard for that, and that led to greater radiation exposure. They were trying to revive the pumps so that in a very orderly manner the reactors could be cooled. What is the other way? To prevent the meltdown somehow, you pump seawater inside. Okay. But seawater, if you do the calculation, it is required in huge volume. The seawater needs to be pumped in huge volume in thousands of liters per second to really cool, because the amount of heat generated is so high, you require thousands of liters per second to really take away so much of heat. So after the accident had occurred, the problem reduces to pumping enough seawater so that the water will evaporate. When the water evaporates, it takes away some heat equivalent to the latent heat of evaporation. See, in studying such failures only, you will get the physical meaning of all the theoretical concepts that you have studied. What is the latent heat of evaporation? Can somebody give the definition? A latent heat of the amount of heat required to evaporate 1 kilogram of water or any material at 100 degrees centigrade to 1 kilogram of vapor at 100 degrees centigrade. That is the latent heat of evaporation of water. So water at 100 degrees centigrade to steam or water vapor 100 degrees centigrade, the amount of heat that is required. That is called the latent heat of evaporation. Where is it physically used? When you pump seawater, you have to calculate how much of seawater is required per minute. There is so much of heat generated. So much of heat is to be carried away. So how much water should I pump? That is the basic engineering question, the basic technical question. To decide how much of water is to be pumped. I can conveniently neglect even the sensible heat part, because in comparison to latent heat, the sensible heat that can be carried away by water is so little. So this is where you get the physical meaning of all the concepts you study in your general physics or engineering. Is it okay? Now I'll stop the Fukushima accidents. Then I'll come to the union carbide issue. The Dow Chemicals or union carbide, the Bhopal gas tragedy. Accident that occurred in India. Lots of people died, lots of people were suffering for their life. Even now, the victims are not yet compensated. There is a political part of it, ethical part of it, the social part of it. It requires equal attention, but let's not go into that. Very, very like a robot, let us confine to the technical aspect of it. Now, what are the major design failures? Because after the accident has happened, see, when people talk about disasters, they say disaster doesn't happen because of a single failure. Disasters happen because of multiple failures. Okay. The Bhopal gas tragedy is a disaster. This, if you analyze in detail, all these exercises or all these accidents are disasters, and you can identify multiple failures. I have not gone into the detail while analyzing the BP oil case. I have not gone into the detail why this particular failure of the blow preventer occurred. That is something that is being investigated even today. Okay, probably after some time the whole details will come out. Why is that failure? What are the multiple? Of course, there are some systemic deficiencies that are pointed out even today. But what exactly happened at the design of the blow preventer that is being proven today, and it will take some time for it to come out. Now coming to the Bhopal gas tragedy, the whole design itself is at fault. The methyl isocyanate, number one, it is an intermediate product in manufacturing a pesticide. Okay, since methyl isocyanate is highly poisonous, people have abandoned that route and then they have redesigned the process in such a way that without coming to methyl isocyanate, the required pesticide can be manufactured. But when they installed the factory in India, in Bhopal, they disregarded the new procedure because it is much cheaper to produce through methyl isocyanate. Number two, methyl isocyanate need not be stored in such huge quantities. In spite of many warnings, they didn't bother to minimize the volume of methyl isocyanate stored in the tanks. So the volume of methyl isocyanate was so huge, okay, and that contributed to the volume of the number of deaths and people injured or affected by the explosion. Number three, there were many safety precautions that were put in place, but none of them were maintained. Many of them were tripped off. Many of the safety procedures were bypassed, leading to such an accident occurring. Number four, the most tragic, even after the accident occurred, okay, the Union Carbide management didn't act. And after it had occurred, it didn't inform the doctors, the local hospital, that such an accident has occurred. This is what is causing the trauma to people, because that would have prevented many deaths. And people didn't know, believe me, that is the tragic part of it. People didn't know in what direction to run. Thinking that they are escaping out of the vicious gas, they were running against the wind, going into regions of greater concentration of methyl isocyanate. That is the level of irresponsibility of the management. You understand? If they run along the direction of the methyl isocyanate, away from that, there is a direction of wind flow. Okay. The plant is located at a particular place. There is a direction of wind flow. Okay. You have to run away from the plant, number one. Number two, you have to run along the direction of the wind. Common sense, is it not? See, this is where the plant is located. I'm sorry I don't have the blackboard. This is where the plant is located. This is how the wind is blowing. Where should we run? If I am located here, I should run here. Do you understand? Away from the plant and along the direction of the wind. If I am located here, if this is the plant, if I am located here, what should I do? I should simply go here, against the direction of the wind. Because the wind has not gathered methyl isocyanate, so I have to simply... So this information could have saved thousands of people. See, methyl isocyanate is flowing in a particular direction. I have to go against the direction of methyl isocyanate, not just the wind. When the wind is coming here, if I am located here, if the wind is coming here, I have to go against the wind. Because this wind has not captured the methyl isocyanate. Only the wind here is doped with methyl isocyanate. Or filled with methyl isocyanate. Not doped. Filled with methyl isocyanate. So even this fundamental idea, even that was not available to the people, and that led to a lot of deaths. Now, to summarize, can you take another 15 minutes, sir? What is the time now? 12. Well, I will just take another 10-15 minutes and then summarize what we have to learn from all this. Next. Now, we have to understand, this is the important part. This is the objective of, these three ideas are the objectives behind giving this exercise to you. Okay, what do you mean by redundancy? Literally, redundancy means, he is redundant, means what? He is not required. It is duplication. Redundancy is duplication to improve the reliability. I'll give you a classic example. We have a data center near the library. The data center is hosting the important service. The server itself costs about 1.52 crores. The important server containing all the university information. So this is a data server. So a server should never collapse. If this data server, if it goes off, then you cannot work in your AutoCAD or Pro Engineer because all these licenses are stored there. If this server is gone means my software will not work. Okay, only when the server is on, so my software will work. Like this, there are many consequences. If the server goes off, there are many consequences. So this server must be available 24/7. So what will we do? We have a UPS. For the server, we have a UPS. What is the purpose of the UPS? Even if the power goes, it will ensure that the server is on, the computer is on. You have a UPS. Now not only that, we have a separate generator also located in the same place. Because I asked a question, probably in another 2 years, that generator might never be used. But still, I want to have a generator. What is the idea? That generator is the redundancy built into the system. It is redundant. It is a duplication. UPS, in most of the cases, will take care. The UPS has a backup for 2 hours. The question is, why do I put switched on for 2 hours, what will happen? Then I should switch on this generator so that my server is on 24/7. On any event, my server should not crash. This is the idea behind redundancy. Probably in another 3 years, that generator will never be switched on. Because what happens, the moment power goes off, what will happen? The UPS will take care of everything. The moment the power goes off, the main generator will be switched on. So the power will be restored. The UPS will go back again. When will this come into play? When will this additional generator come into play? Power goes off. Power goes off for 2 hours, and for 2 hours the main generator is not switched. This event may not happen at all, but still we do have such a system in our campus. This is the idea behind redundancy. Any critical system must be protected with enormous amount of redundancy. Any critical system that you have, it must be protected with very high amount of redundancy. I don't know if you have you ever visited a ship? Okay, one of the important issues in marine engineering is if something happens to my ship in the mid-sea. Okay, if something happens to my ship in the mid-sea, suppose one bolt in the propeller shaft, it has broken. Okay, the entire ship has to be stopped because it is a very critical bolt. That bolt had failed. Okay, now that bolt needs to be replaced. Now can I stop the ship, go to the shop, buy a bolt and then come back? In the mid-sea, no such thing could happen. Okay, so the entire spare part for the ship, the entire spare part, including the main shaft itself, it will be available within the ship. Including propeller, including main shaft, for everything they will have. Of course, aeronautical engineers, they don't have such a luxury. Okay, they cannot say that I will have spare part for everything. What should they do? It is not good enough that they should have spare part. They should design things in such a way that the system doesn't fail. Hey, marine engineers will have only spare parts. That is good enough for them. But when you design aerostructures, you should design it in such a way that. So that is why, see, I have talked about, okay, come back. Any aircraft, generally, a single engine aircraft is inferior when compared with a twin engine aircraft. Can somebody say why? Because when one engine fails, a single engine aircraft is just like a piece of stone. Okay, it can do. It has some services, so you can try to manipulate the services of them. You can try to glide, but it may not happen most of the time, unless you are in very favorable situations. So it is almost a piece of stone. But when you have multiple engines in aircrafts, you can try to still control the mission. The idea of multiple engines is redundancy. Do you understand? The idea of having multiple engines is redundancy. Having an inverter at home is redundancy. You don't want to lose power even when there are official power cuts. You build in redundancy into your system. Having a UPS for a computer, having an additional stabilizer for all the appliances, again the idea of redundancy. Any equipment, be it a refrigerator or a television, they come with a built-in stabilizer. But still you would like to have an additional stabilizer. Why? You want to have a redundancy in the system. You understand what we mean by redundancy? This is an idea which you may have to build in. Okay, well, why is it important? Now, we have studied in detail about the failure of the blowout preventer. Now, the designer should have asked, what is the purpose of the blowout preventer? To prevent the blowout. Simple. What would have happened? What will happen if the blowout preventer itself had failed? That is the idea behind. That is the idea behind redundancy. So to put it in a philosophical plane, there is a very interesting question. Okay, who to God the gods? Who to God the gods? That is the idea behind redundancy. Let's go to the next issue, factor setting. Okay, so this is a beautiful cliff. Okay, I have a close-up view. Next slide, please. I have a close-up view of the same cliff. Now there is a person sitting there. Imagine that it is you. Now my question is, why are you sitting here? Why not here? No, if it is you, where will you sit? Okay, either here or here. Depends on two things. Okay, depends on two things. If it is me, where will I sit? It depends on two things. One, can you please go back? This depth. If it is very large, probably I'll go here. Number two, my mental makeup. Okay, if I am very adventurous, probably I'll move closer to the cliff. If I am very conservative, I'll go away from the tip. Understood? Any difficulty? Now let us come to engineering. What is factor of safety? Now, many materials fail. However you design it, things are bound to fail. If you ask me how exactly failure takes place, I am gone. Okay? If you ask me how exactly a material, a metal, let us take steel, how exactly a steel component fails, if you ask me, then I have to talk a lot. It's not that easy. Okay? I used to, when we were in a discussion, I was there in a company and I was telling the MD of that company, I mean, doctors say that why death in human being doesn't take place. Okay, many times they don't know the exact cause of death. Forget about human beings. Even in materials, we don't know why exactly the failure takes place. See, you later on, in your higher semester, you study what is called theories of failure. You study what is called? There is a catch. Please say it aloud. Theories of failure. Do you see any pun in it? Do you see anything to laugh about it? There are a lot of things to laugh about it. If there is a theory of failure, you can understand. But when I say theories of failure, that means what? I have not understood it fully. If I say theory of failure, what does it mean? It means I have identified a theory why failure takes place. When I say theories of failure, I myself correct. There is no single theory. I have multiple explanations. What is the meaning of multiple explanations? Multiple explanations is acknowledging that I don't know. I don't know exactly, at least. We know, but we don't know precisely. We don't know exactly. Okay? So you will study definitely, please don't worry, about theories of failures. But all that I'm trying to convey now is, I don't know why exactly a failure takes place in a material. Suppose, say, let me take a simple case. Steel fails when the tensile stress induced reaches 300 megapascals. I repeat my statement, please listen carefully. Okay, please listen carefully. I say steel fails when the tensile stress crosses 300 megapascal. Clear? Steel fails, low carbon steel to be more precise, fails when the tensile stress crosses 300 megapascals. Now, I am designing, say, a particular component. Will I allow the stress in the component to come to 300 megapascal? That is equal to sitting here. Might fall. You get my point? If I allow the stress in my component to come to 300 megapascal, that is almost equal to coming and sitting here. So what I will do is, I will never allow the stress to reach 300 megapascal. What will you do? How much will you allow? How much? Give me a value. 200 gigapascal. 200 megapascal. Or he may decide 250 gigapascal. He may decide 270 megapascal. Sorry, everything is megapascal. 270 megapascal. Because at 300 it is going to fail. He may say, no, it should be 200 megapascal. How to decide it? Again, it depends on two things. Number one, how critical the component is. If the component failure means something very, very serious, then I should design it. If the fall is going to be very serious, then I'll be far away from the cliff. I'll be far away from the 300 megapascal. Number two, the approach of the designer. If the designer is going to be conservative, he will go away from 300. He will be very low from 300. If the designer is adventurous, he will try to come. There are many other factors influencing the factor of safety. Now, the factor of safety is nothing but the ratio behind the stress at which failure occurs and the stress up to which we are going to handle it. Factor of safety is nothing but 300 divided by 200 for him, 250 for him. You understand? That is the level, that is a measure of how far away I want to be away from the cliff. I am making it clear. I don't want to, if factor of safety is 1, then what is the stress up to which I will allow? I will allow up to 300 megapascal. If the factor of safety is 2, what is the stress up to which I will allow? No, be careful. 150. 300 by 2. It is up to 150 that I will allow the component to be loaded. 150 megapascal. If the factor of safety is 3, it is. If it is a very critical component, how will you choose the factor of safety? If it is a very critical component, it should not fail at all. Should the factor of safety be high or low? Any doubt? The factor of safety will be very high if the component is very critical. If I use the failure of Titanic, okay, the factor of safety comes into play. Okay. And there are certain issues. The failure of Titanic is also the question of redundancy comes into play. The regulation at that point of time say that it is enough if you have only so many number of lifeboats. They have followed the law. But at least, should I not have the number of the lifeboat capacity to be equal to number of passengers? In fact, the lifeboat capacity must be more than the total number of... That is the idea behind redundancy. Because it is lifeboat. You cannot say I don't have space. Okay, you are in waiting list, you cannot say when it is a question of lifeboat. Okay, so in the lifeboat, you should have had redundancy, but they didn't even have the required number of seats. Is it okay? Now, so that is the idea behind the concept of redundancy and the idea of factor of safety. Next slide, please. Next. Now, there is something called fail-safe design and safe-fail design. This is the third concept that I wanted to convey through these cases. What is fail-safe? I have designed it in such a way that it will never fail. I have used high factor of safety, high values of factor of safety. I can guarantee that my system will not fail. Good. I am happy. But I am not happy enough. I'll ask back. Does your system have a safe fail mechanism? So, we can understand what is fail-safe. Fail-safe means it will never fail. What is a safe fail mechanism? A safe fail mechanism is, see, I know with my experience in life, I am very skeptical. I know that every system does fail. When it fails, how is it going to fail? Is it okay? I know while walking, I know I should not fall down. Okay? But if I am to fall down, I'm sorry, I'm not referring to you. If I am to fall down, how will I fall? I will fall in such a way that, okay, my head is protected. You understand? I say, I don't want to fall. No, I don't want to fail. But even when you fail, because failure is inevitable, even when you fail in such a way that the critical components remain unaffected. If somebody is going to push me down, when I am walking just like this and then somebody is going to shove me like this, what will I do instinctively? Instinctively, my hands will come so that all the shock is absorbed by strong parts, not by my head or by my chest. Does it happen instinctively? Okay. So, this is what we mean by safe fail. Okay. In your electrical system, you don't want, do you want, when you design your system, do you want a failure to happen? No. But why are you providing a fuse? You provide a fuse or an MCB because if at all there is an excess flow of current, the failure will take place, not my electrical line will burn. Otherwise what will happen? If there is excess flow of current, what will happen? My line will burn. It might burn here. The wire might burn. It may lead to, it may catch fire. The curtain may catch fire or some other material may catch fire and it may lead to a disaster. So what do? Along the line, I keep very consciously a fuse. What is the function of a fuse? The fuse, when there is excess current, it will melt and it will trip the rest of the system. The current will not flow to the rest of the system. What is the function of an MCB? MCB is, I don't know. Probably you can go there and see. It will be. Can someone open? Let's not open it. We don't have time also. MCB you can see. Okay. MCB is something which will trip when there is an excessive current flowing through the system. In mechanical systems also, we have something called shear pinch. An equivalent of fuse. The shear pinch, they will fail instead of allowing something to fail. So, you design in such a way that no failure takes place. But not only that, you should also design in such a way that we should also design in such a way that if at all a failure is going to take place, that will take place in a place convenient. A place where it doesn't affect the whole system adversely. Is it okay?
Talking about the redundancies, I just got one point. There is, you know about the railway locomotives, right? So what happens is, in our channel we use electrical multiple EMU that works on the electrical power, right? So what happens when you go out of deep south is that you will be having the diesel engine. Okay? So the diesel engines, they don't power the axles directly, right? So what happens is, inside the engine you have a diesel engine which is driving a generator, right? So that generator in turn will power the motor. Okay? So what happens is, it's a kind of hybrid engine, right? So in case of a diesel engine, what happens is you have a set of 2 or more diesel engines inside the locomotive, right? So what happens is, even if one set of engine fails, you can run with the help of other set, right? So this is a case of redundancy which I wanted to tell you. And to start with the assignment question, we just have a brief video about the fourth window getting failed. This is just a real-time video, right? So what happens is, a car from the behind, just traveling at a speed of 30 miles per hour, which is roughly 45 kilometers per hour, right? So this is a very slow speed as compared to the US standard regulations. The maximum limit for a car is 60 miles per hour, which is nothing but 90 kilometers per hour, right? So the problem is, the thing is, at a very low speed, when you have a rear-end collision, okay, so what happens is, there is a chance of catching of fire. Okay? Go to the slide. So this is a very big failure in the automobile industry, especially in the car from Ford. Okay? So the history is, the Ford Motor CEO in the year 1968, they decided to introduce a subcompact car. They wanted to make it cheap, and also it was designed at a very short span of time, and they wanted to introduce a car very quickly, right? So the salient features of the car was, it was a very subcompact car. The size and weight was really low and compared to the existing lineup in the market, right? And also it was a low cost car because it was a very subcompact car, right? And with regard to all the things, that is the initial price, the fuel consumption, and their reliability, etc. And the next point is, with regard to the appearance, the comfort features and all, they wanted to be somewhat superior, right? And as I told you, it was released in a very short span of time. Yes. So as you've seen the video, the main problem with the car was the fuel tank was getting ruptured and there was a rear-end collision. Okay, this was a major problem, and the reason was the fuel tank was placed between the rear-end bumper and the axle. So the axle is, the rear axle. Okay. So when there was a collision, the fuel tank was crushed and the fuel inside the fuel tank was released, which eventually caught fire because of the friction between the moving metals because of collision. Okay. And also the fuel filler pipe, that is, the fuel tank will be at some lower level, right? And there will be a fuel filler pipe which is coming to the body of the car, right? So the problem was the filler pipe was getting ruptured first. That caused the spillage of fuel from that particular rupture point. Okay? And also there was a structural problem with the doors, right? So when there was a collision, the doors got jammed, And next point is the floor plan. Floor plan is nothing but structural part of a car consists of two things, namely the frame and the body. Right? So the frame will be the basic part of a car, right? Over which you will have sheet metals covered. Right? So the problem was you have three main components. There is the engine part, the front part, and then the middle part will be the passenger compartment, and then the rear end. Okay? So these parts will be covered by floor, sheet metal. And in this case, it was separated. So what happened was when there was a collision, this separated part will be connected by very, it's a kind of mean connection, because of which the floor plan got separated, and the fuel or the fire which it used to enter the passenger compartment easily. Okay, so this was a very major problem, and also the passenger inside the passenger compartment could not come out because of the door jam problem. Next slide. So this is a typical layout. You can see that there is a rear end bumper, and you have the fuel tank. Okay. So this is the rear axle. So the rear axle is a very fixed component, that is a very rigid component of a car. And what happens is, whenever there is a rear end collision, the fuel tank is to get compressed and it just goes in. Okay. So, next slide. So the possible suggestions for, before going to the suggestions, the main reason they went out to place the fuel tank there was, if you just place it above the axle, what happens was the rear end trunk space would have been reduced greatly, because you need to keep some luggage at the rear end, right? So that is the reason why they wanted to go for they wanted to place the fuel tank between the bumper and the rear end, right? So the possible solution could be to compromise for the boot space and keep the fuel tank above the rear end. And then they could have followed a uniform floor plan, but body in white is nothing but it's a combination of frame and the body. Okay, so that is a new end. From 1980s onwards, they started to build cars using body in white. That is nothing but the frame and the body will be of, it's a singular unit. Okay, so at that time it was not a big trend, but now it is a trend for the modern days car. Okay. And also they could have redesigned the doors such that they don't jam because of the collision. So this is a typical body in white. There is nothing but it's a combination of frame and body. Right? So this particular projection is the frame part, and the sheet metals are just included in it. Okay? And this is nothing but the passenger compartment's floor, and we have a similar floor above the rear axle or the boot space. Right? So there was a gap between this floor plan and the boot space, which used to get ruptured, and the fire which got during the collision used to enter into the passenger compartment. Next. So this is a Mercedes AMG's body. Okay. So you can see that this is a diagram for side impact. Okay. So the orange arrow indicates the force with which an external body is going to impact on the car, and the green ones are the force distribution among the body. Okay. So you can see that now there is a collision, the force gets distributed along all the parts of the structural components. Right. So this is one example of modification to the frame on the chassis component. Okay. This is a crash test of Ford Pinto, okay, after eventual failure of his model. motion of 47, you can see that fuel is getting spilled up because of the collision. Okay. Stop there. That fire was caused by the friction during the moving metal part. So this is a camera which is kept at the bottom of the testing track. Okay. Example of the unit design, and you can say that the after effect was there was a financial lawsuit against the company to compensate for the accidents that you suffered because of this faulty design. Right? So that's it for the fourth intro design.
From the pilot line, first our deputy sir have taken the class very nicely for me. Master, let this class may not get fight. Okay, I'll take 2 or 3 minutes taking a simple concept, and I'm having a video that will be explaining a better explanation of the pilot, that is Tacoma narrow bridge. Okay, this Tacoma narrow bridge is located in Washington, which connects the Tacoma head. Yeah, it connects Tacoma with and creates a peninsula. That is the small history of this Tacoma narrow bridge. It is a bridge of length 5,000 feet. They spent millions of dollars to construct this bridge, and the demand was to have a short route from these 2 places. There was the demand. So another thing which was in contradiction was the car. So they went with theoretical design without any practical knowledge. They went with the theoretical design, and they constructed the bridge with the theories available with them. Okay. The main reason for this failure is a term called resonance. Okay. We all know about it. That is, we are having the air is moving with some frequency, and the bridge which is constructed, it is having some natural frequency. Okay. And when this 2 frequency matches, a process called resonance occurs. Okay. That is what here occurs can happen in the Tacoma bridge. That is the frequency of the air moving around the bridge and the natural frequency of that bridge, it matches, and the resonance occurs. Okay. And one more thing is that the width of the bridge, the width to span ratio. The span is the length between the 2 columns. Okay. The ratio was 2. So these are the 2 concepts. These are the 2 main concepts for that Tacoma bridge failure. I'll put a video which will be clearly explaining the failures of this Tacoma bridge. Listen, see it carefully. It is having a torsional motion. Okay, it is twisting motion. The whole bridge twists for a minute and it fades. The velocity of the bridge was 42 miles per hour at that time. You can imagine 42 miles per hour. It's 60 kilometers per hour. There was no life loss except a single dog. Dog died. See the torsional motion. One part of the bridge is rotating clockwise direction, while the other part is in anti-clockwise direction with respect to the center line. To the ground, it is getting snapped due to the velocity of the, see the diameter of the cable. The other part is not visible. We have drilled this holes, the air would have passed through the meshes so that the process of resonance will not occur.